Welcome to the AI podcast. I am your host, Alex, and today I am genuinely thrilled about this conversation. We're diving into something that honestly I think is one of the most underappreciated challenges in the entire AI industry. We're talking about data pipelines, not the sexy part of AI, right? Not the model architecture, not the breakthrough paper, but the infrastructure that actually makes all of it work. And joining me today is someone who has been in the trenches building this stuff at some of the most demanding AI companies on the planet. Priya Ramanathan, VP of AI Platform at Nexus Data Systems. Priya, welcome to the show.
Thank you so much, Alex. It's really great to be here. And I have to say, you just touched on something that is near and dear to my heart. The fact that you called data pipelines underappreciated, that is the story of my career in a nutshell.
Well, let's change that today. Before we dive into the deep technical stuff, I'd love for our listeners to get to know you a bit. You have had an incredible career arc. You've been at Databricks, Anthropic, and now you're running AI platform at Nexus. Can you give us the quick version of how you ended up here?
Sure. So I started my career as a data engineer at a mid-sized fintech company. And this was back in the early 2010s when big data was still the hot buzzword. I was building ETL pipelines before most people even knew what ETL stood for. And I realized pretty quickly that data engineering was this invisible force multiplier. Every team needed it. Nobody wanted to fund it. And the people who did it well were the unsung heroes of the organization.
That resonates so much. It's like the plumbing of technology, right? Nobody thinks about it until something breaks.
Exactly. And that metaphor actually goes deeper than people think. Because just like plumbing, when a data pipeline breaks, it's not just an inconvenience, it can be catastrophic. Imagine you're running a fraud detection model at a major bank, and your feature pipeline has a silent failure. The model is still running, still making predictions, but it's working with stale data, or worse, corrupted data. And you don't know it. You find out 3 days later when losses spike and your VP is asking what happened. That's the kind of scenario that keeps data platform people up at night.
That's a terrifying scenario. And I assume that's not hypothetical. That's based our real experience.
Unfortunately, yes, multiple times at different companies, and it's actually more common than people think. The industry has gotten really good at building models, but we haven't matched that capability with the infrastructure to feed those models reliably, monitor them continuously, and catch failures before they become business-critical incidents.
So let's talk about scale for a moment. When you say data pipeline at a company like Nexus, which is processing AI workloads for enterprise clients, what does that actually look like in terms of scale?
So at Nexus, we're processing roughly 2 billion events per day across our client base. That data comes in from dozens of different sources in different formats at different frequencies. Some of it is real-time streaming data. Some of it is batch data that arrives once a day. Some of it is semi-structured logs that need heavy parsing. And all of it needs to be transformed, validated, enriched, and delivered to the right models at the right time. When I say pipeline, people sometimes imagine a simple flow from point A to point B. But in reality, it's more like a living, breathing organism with hundreds of interconnected flows, each with their own SLAs, their own failure mode, and their own downstream dependencies.
So Priya, let's peel back the layers on this. When you talk about the hidden complexity of data pipelines, what are the things that most teams get wrong when they're first building out their ML infrastructure?
Oh, where do I start? Okay, so the number one mistake I see is treating the data pipeline as a static system. Teams will spend months building this beautiful, handcrafted pipeline. They'll test it thoroughly, they'll deploy it, and they'll think they're done. But the reality is, a data pipeline is a living, breathing system. It needs to evolve constantly. The schemas change, the data sources add new fields, the upstream providers change their APIs without telling you. And if your pipeline isn't built to handle that kind of change gracefully, you're going to have a bad time.
It sounds like a lot of the challenge is at the boundaries, right? Where your system meets the outside world.
That's exactly right. The boundaries are where everything breaks. And I'll give you a concrete example from my time at Databricks. We had a customer, a major retail company, and they had built this really sophisticated recommendation engine. Beautiful model, state of the art. But their data pipeline was ingesting product catalog data from about 40 different suppliers. And one day, one of those suppliers changed their date format from American style month, day, year to European style day, month, year. No announcement, no heads up, just a quiet change on their end.
Oh no.
Yeah. And here's the thing. The pipeline didn't break. That's what's scary. If it had thrown an error, someone would have noticed. Instead, it silently parsed all those dates wrong. So suddenly products that were supposed to be seasonal were being recommended year round. Products with expiration dates were being served after they should have been pulled. It took them 3 weeks to figure out what happened. 3 weeks of damaged customer trust and lost revenue.
That is terrifying. And it really illustrates why just having a pipeline that runs isn't enough. It has to be a pipeline that runs correctly.
Right. And this is where the concept of data contracts comes in, which I'm a huge advocate for. A data contract is essentially a formal agreement between the producer of data and the consumer of data. It specifies the schema, the semantics, the freshness requirements, the quality thresholds, everything that both parties need to agree on for the system to work correctly.
It's like an API contract, but for data.
Exactly. And just like API contracts, they need to be versioned, they need to be enforced, and there need to be consequences when they're violated. At Nexus, we've implemented what I call strict contract enforcement. If an upstream data source sends us data that violates its contract, we don't silently accept it. We reject it, we alert the team, and we gracefully degrade. We might serve stale data from cache, or we might disable a specific feature that depends on that data, but we never let bad data silently flow through.
That requires a lot of maturity and discipline, though. I imagine a lot of teams push back on that approach because it feels like it adds friction.
100%. And I get it when you're a startup and you're moving fast and you just need to ship. The idea of setting up formal data contracts feels like overkill. But here's what I tell those teams. The pain of setting up contracts now is nothing compared to the pain of debugging a production model that's been silently degrading for weeks because some upstream data changed. I've seen that story play out dozens of times, and it never ends well.
You mentioned schema changes as a big source of problems. What about the actual content of the data, like the values changing, even when the schema stays the same?
Now you're talking about data drift, and this is where it gets really interesting. Schema changes are the easy part, honestly. They're loud, you can detect them with basic validation. Data drift is the silent killer. It's when the statistical distribution of your data changes over time, but the format looks exactly the same. Your pipeline keeps humming along, everything looks green on the dashboard, but the data your model is seeing in production looks nothing like the data it was trained on.
Can you give us an example of that in the wild?
Sure. Think about a fraud detection model. You train it on historical transaction data. The model learns patterns like large transactions from new accounts are suspicious, or transactions from certain geographic regions have higher fraud rates. But then the world changes. A pandemic hits, and suddenly everyone is making large online purchases from their homes. The behavioral patterns that your model learned are no longer valid. The data distribution has shifted. And if your pipeline doesn't detect that drift and trigger a retraining cycle, your model is going to start missing real fraud while flagging legitimate transactions.
That's such a clear example. And it's not a hypothetical. That actually happened to a lot of companies during COVID.
Oh, it happened to nearly everyone. The companies that survived were the ones that had drift detection built into their pipelines. They had automated monitoring that would flag when the distribution of key features shifted beyond a certain threshold. And critically, they had automated or semi-automated retraining pipelines that could kick in and adapt the model to the new reality.
All right, so we've talked about the complexity and the drift. Let's get into the war stories now. Priya, you mentioned cascading failures earlier. I want to hear about a time when data quality issues actually broke something in production. Give us the real story.
Oh, I have so many. But let me tell you about one that still haunts me. This was at Anthropic. We were training a new version of one of our language models, and the training run was going to take about 2 weeks on a massive GPU cluster. We're talking millions of dollars in compute. And about 4 days into the training run, one of our researchers noticed that the loss curve was behaving strangely. It was converging, but not as fast as our simulations predicted. Something was off.
Uh-oh, 4 days into a 2-week training run. That's a lot of compute already burned.
Exactly. So we started investigating, and after about 16 hours of debugging, we traced it back to a subtle issue in our data deduplication pipeline. We had a pre-processing step that was supposed to remove near duplicate documents from the training corpus. The problem was that a recent update to one of our text normalization libraries had changed how Unicode characters were handled. Specifically, some non-breaking spaces were being treated differently.
You're kidding. Non-breaking spaces?
I wish I were kidding. That tiny change meant that our deduplication algorithm was failing to catch about 8% of the near duplicates. So the model was being trained on a corpus with significantly more redundancy than intended. The model wasn't broken, it was just learning less efficiently because it was seeing the same content multiple times in slightly different forms.
And by the time you found it, 4 days of training time were essentially wasted.
Well, not entirely wasted. We were able to resume from a checkpoint. But we had to regenerate the entire training data set with the corrected deduplication, which took another day and a half, and then restart the training from an earlier checkpoint. All told, we lost about 5 days. Millions of dollars because of non-breaking spaces.
That story really drives home a point that I think is so important. In AI systems, data quality isn't just about getting the right answer. It's about efficiency, it's about cost, it's about opportunity cost. What else could your team have been doing with those 5 days?
That's the right way to think about it. And honestly, that incident was a turning point for us. After that, we implemented what I call the data quality pyramid. It's a framework I developed for thinking about data quality in layers. At the base, you have structural quality. Does the data conform to the expected schema? Is it complete? Are the types correct? That's your table stakes.
Okay, so that's like the foundation.
Right. The next layer of is semantic quality. Do the values make sense? Are the dates within reasonable ranges? Are the text fields in the expected language? Are there any logical contradictions? This is where you start catching things like that date format issue I mentioned earlier.
And I imagine this is where statistical validation comes in.
Exactly. The third layer is distributional quality. This is where you're checking whether the statistical properties of your data match what you expect. Are the feature distributions stable? Are there unexpected correlations appearing? Has the class balance shifted? This is your drift detection layer.
What's at the top of the pyramid?
The top is what I call task-specific quality. This is where you evaluate whether the data is actually useful for the specific task you're trying to accomplish. You might have data that passes all the structural, semantic, and distributional checks, but it might not contain enough signal for your model to learn what it needs to learn. This is the hardest layer to automate, but it's arguably the most important.
Hey, do you have a good example of that top layer failing?
Yeah, actually, at Nexus, we had a team building a customer churn prediction model. The data looked great on paper, clean schemas, no drift, all the standard checks passed, but the model's performance in production was terrible. It turned out that the feature engineering pipeline was using a rolling 30-day window for aggregating customer behavior. And for their specific use case, the signals that predicted churn were actually happening in a much shorter window, like 3 to 5 days before the customer left. The 30-day window was smoothing out exactly the signals the model needed.
So the data was technically correct, but it was the wrong view of the data for that specific problem.
Presley, and no amount of automated quality checks would have caught that. It required a human to step back, look at the business problem, and ask whether the features they were generating actually made sense for the task. This is why I always say that data quality is not just an engineering problem. It's a cross-functional problem that requires collaboration between engineers, data scientists, and domain experts.
That's such an important point. The technology alone isn't enough. You need the organizational structures and the culture to support it.
Absolutely. The best data pipeline in the world is useless if the team using it doesn't understand its limitations and doesn't know how to interpret the quality signals it's sending them.
Okay, so we've established that data quality is this multi-layered challenge and that things can go wrong in really subtle ways. That naturally leads to the question of, how do you even know when something is going wrong? Let's talk about observability. What does it mean to have observability in your ML systems?
Yeah, this is probably the area I'm most passionate about right now. So observability in the traditional software engineering sense is about being able to understand the internal state of your system by looking at its external outputs, logs, metrics, traces, that kind of thing. But for ML systems, observability needs to go deeper. You need to monitor not just whether your system is up and running, but whether it's behaving correctly. And correct behavior in an ML system is much harder to define than in a traditional application.
Because correct isn't just, did the API return a 200 status code?
Right. Your model can return a perfectly valid response every single time and still be completely wrong. A classification model can confidently assign a label to every input it receives, and if the data has drifted, those labels might all be garbage. The system is technically healthy, the model is fundamentally broken, and your standard monitoring tools won't tell you the difference.
So what do you actually monitor? What does ML observability look like in practice at Nexus?
We think about it in 3 layers. The first layer is infrastructure observability. This is your standard stuff: CPU utilization, memory usage, latency, throughput, error rates. You need this. It's table stakes, but it's not sufficient. The second layer is data observability. This is where you're monitoring the data flowing through your pipelines. You're tracking things like schema changes, null rates, value distributions, freshness, volume. Is the data arriving on time? Is it complete? Does it look like what we expect?
And that ties back to the quality pyramid you mentioned earlier.
Exactly. The data observability layer maps pretty directly to the first 3 levels of the pyramid. And then the third layer, which is the one most companies don't do well, is model observability. This is where you're monitoring the model's actual behavior in production. Prediction distributions, confidence scores, feature importance drift, output calibration. You want to know not just what the model is predicting, but whether those predictions make sense in context.
How do you handle the alert fatigue problem? Because I imagine with all of those monitoring signals, you could be drowning in alerts.
Oh, alert fatigue is so real. And it's actually one of the biggest challenges in ML observability. If you set naive thresholds on every metric, you're going to get hundreds of alerts a day, and your team will start ignoring them. We've invested heavily in what I call intelligent alerting. Instead of setting static thresholds, we use adaptive baselines. We train lightweight models on the historical behavior of our metrics and alert when something deviates significantly from the expected pattern. So instead of saying, alert me if latency exceeds 200 milliseconds, we say, alert me if latency is behaving anomalously compared to this time last week, accounting for day of week and seasonal patterns.
That's clever. You're using ML to monitor your ML. Very meta.
Yeah, it is a bit recursive, but it works really well. We've reduced our false positive rate on data quality alerts by about 70% since we moved to this approach, and the alerts we do get are much more actionable because they're telling us something genuinely unexpected is happening, not just that a metric crossed an arbitrary line.
What about the human side of this? Like when an alert fires, what's the workflow? Who responds and how do they triage it?
Great question. So we have a concept of data on-call similar to traditional site reliability engineering. We have a rotating on-call engineer who is responsible for responding to data quality alerts. When an alert fires, the first thing they do is check our observability dashboard, which gives them a unified view of all three layers: infrastructure, data, and model. They can see whether the issue is a pipeline failure, a data quality degradation, or a model performance drop, and they can trace the causality chain. Often, a model performance drop is actually caused by a data quality issue, which is caused by an infrastructure failure upstream.
So the observability layers let you trace the root cause, not just see the symptom.
Exactly. And we've built a lot of tooling to make that root cause analysis faster. We have automated correlation analysis that says, hey, your model performance dropped on this segment of users, and it correlates with this feature's distribution shifting, which correlates with this upstream data source having a delayed delivery. So instead of the on-call engineer spending hours manually correlating dashboards, the system does most of that analysis automatically and presents them with a hypothesis.
That sounds incredibly powerful. How long did it take to build out that kind of observability infrastructure?
Honestly, it's been a multi-year journey, and we're still iterating. The first version was pretty basic, just some Grafana dashboards and PagerDuty alerts. But over time, we've layered on more sophistication. I'd say it took us about 18 months to get to a point where we were genuinely confident in our ability to detect and diagnose issues quickly. And the key insight was that you can't build it all at once. You have to start with the most critical pipelines, instrument them thoroughly, and then expand outward.
Start where it hurts the most.
Exactly. Start where the business impact is highest. For us, that was our core personalization pipeline, because a degradation there directly impacts revenue. Once we had that instrumented and our team had built the muscle memory of responding to alerts and triage, we expanded to the rest of our pipelines.
So Priya, let's shift gears a bit and talk about something that is generating a lot of buzz right now: synthetic data. It seems like everywhere I look, there's a new startup or a new research paper claiming that synthetic data is going to solve all of our data problems. What's your take on this? Is it hype or is there real substance here?
This is such a good question. And I think the honest answer is it's both. There is absolutely real substance to synthetic data. It is genuinely useful in specific scenarios and can be transformative. But there's also a lot of hype. And I worry that some teams are reaching for synthetic data as a shortcut when what they really need is better data infrastructure.
Let's start with the substance. Where does synthetic data genuinely add value?
So there are a few scenarios where synthetic data is incredibly powerful. The first is when you have a data scarcity problem. Let's say you're building a model to detect a rare type of manufacturing defect and you only have 50 real examples. That's not enough to train a robust model. But if you can generate thousands of realistic synthetic examples of that defect, you can bootstrap your model's performance significantly.
Makes sense. What else?
The second scenario is privacy and compliance. There are domains, healthcare, finance, certain government applications, where you simply cannot use real data for development and testing because of regulatory constraints. HIPAA, GDPR, you name it. Synthetic data that preserves the statistical properties of the real data without containing any actual personal information is a game changer in those contexts. We use this approach at Nexus for any pipeline development that involves personally identifiable information. Our engineers never touch real user data. They develop and test against synthetic data sets that have the same distributions, the same edge cases, the same complexity, but contain zero real information.
That's brilliant. From a compliance perspective, I imagine it also speeds the development because you don't have the overhead of access controls and data handling procedures for every developer.
Exactly. It's a massive developer productivity unlock. Our engineers can spin up a realistic test environment in minutes instead of going through a 3-day access approval process. But here's where I want to provide a counterbalance. Synthetic data is not a replacement for real data. It's a complement. And I've seen teams make the mistake of over-relying on synthetic data, especially in the training phase. The problem is that synthetic data, by definition, is generated from a model's understanding of the real world. And that understanding is imperfect. There are going to be edge cases, correlations, and patterns in the real data that your synthetic data generator doesn't capture.
So there's a risk of your model learning the synthetic distribution instead of the real world distribution.
Presley, we call this the synthetic ceiling. There's a point at which adding more synthetic data doesn't improve your model's performance on real-world tasks. And if you're not careful, you can end up with a model that performs beautifully on synthetic benchmarks and falls apart in production. I've seen this happen. A team at a previous company trained a computer vision model almost entirely on synthetic data. It achieved amazing accuracy on the synthetic test set, 98%. In production, it was struggling to break 70 because the synthetic images didn't capture the messy reality of real-world conditions. Lighting variations, occlusions, motion blur, all the stuff that's hard to synthesize perfectly.
So what's the right approach? How do you blend synthetic and real data effectively?
The approach we've landed on, and I think is the emerging best practice, is what I call the synthetic sandwich. You start with real data as your foundation. This is your ground truth, your source of real-world signal. Then you augment with targeted synthetic data to fill specific gaps. Maybe you need more examples of rare edge cases, or you need to balance an imbalanced data set, or you need to stress test against failure scenarios that rarely occur in the wild. And then you validate everything against a held-out set of real data. Never, ever benchmark your model only against synthetic data.
The synthetic sandwich. I love that. That's going to stick with people.
I hope so. But there's one more dimension to this that I think is really exciting, and it's where I think synthetic data is going to be truly transformative, and that's evaluation and testing. One of the hardest problems in ML engineering is generating comprehensive test suites for your models. In traditional software, you can write unit tests and integration tests, but for ML models, defining what correct behavior looks like is much harder. Synthetic data lets you generate parameterized test cases. You can systematically vary specific attributes and verify that your model behaves correctly across the full space of possible inputs.
So it's not just about training. It's about building confidence in your model's robustness.
Exactly. At Nexus, we generate synthetic evaluation sets that are specifically designed to probe for known failure modes. We call them adversarial scenarios. What happens when this feature is missing? What happens when these two features have an unusual combination? What happens when the input is at the extreme of the distribution? Synthetic data lets us test all of that systematically in a way that would be impossible with just real data.
All right, Priya, we're coming up on the end of our conversation, and I want to look forward. You've given us this incredible view of where we are today with data pipeline infrastructure. But where are we going? What does the next 5 years look like in this space?
Yeah, I think about this a lot, and I'm genuinely excited about where things are headed. I think we're going to see three major shifts in AI infrastructure over the next 5 years. The first is what I call the declarative revolution. Right now, building and maintaining data pipelines is largely an imperative exercise. You write code that says do this, then do that, handle this error this way. It's detailed, it's brittle, and it requires a lot of specialized engineering talent.
And you think that's going to change?
I think it has to change. The demand for ML infrastructure is growing exponentially, but the supply of engineers who can build and maintain it is not keeping pace. So we're going to see a shift toward declarative pipeline definitions. Instead of writing code that says how to process the data, you'll write specifications that say what you want the data to look like when it's done. The pipeline orchestration system will figure out the how. It's similar to what SQL did for databases. You don't tell the database how to join two tables. You tell it what you want, and the query optimizer figures out the execution plan.
That's a really compelling vision. But it sounds like it requires much smarter orchestration systems than what we have today.
It does. And that's where I think large language models are actually going to play a transformative role, ironically, in building the infrastructure that powers other large language models. Imagine an orchestration system that can understand your declarative specification, generate the pipeline code, optimize it for your specific infrastructure, and even automatically diagnose and fix issues when they arise. We're already seeing early versions of this. At Nexus, we have internal tools that use LLMs to help engineers write and debug pipeline configurations.
ML, building the tools that build ML. Very recursive.
Ha! The recursion never ends in this field. But seriously, the second big shift I see is around data provenance and lineage becoming a first-class concern. Right now, most organizations have a vague sense of where their data comes from and how it's been transformed. But as AI regulations tighten and as models become more consequential in people's lives, there's going to be a legal and ethical requirement to have complete traceability from the raw data source all the way through to the model prediction. Every transformation, every aggregation, every filtering step needs to be documented and auditable.
Like a chain of custody for data.
Exactly that. And the tooling for this is still pretty immature. We need something like Git for data pipelines. Full version history, branching, diffing, the works. Some companies are working on this. Tools like DVC and LakeFS are making progress, but we're still early. In 5 years, I think data provenance will be as standard as version control is for code today.
And the third shift?
The third shift is the blurring of the boundary between data processing and model training. Right now, these are treated as two distinct phases. You process your data, you store it, and then you train your model on it. But I think we're moving toward a world where data processing and model training happen simultaneously and continuously. Your pipeline isn't just feeding a static training set to a model. It's continuously streaming new data. The model is continuously learning, and the pipeline is continuously adapting based on the model's feedback.
Continuous learning in the truest sense.
Yes, and this has massive implications for infrastructure. You need systems that can handle both the data engineering workload and the model training workload in a unified framework. The batch versus streaming distinction that we deal with today feels like it's going to collapse. Everything will just be continuous.
Priya, this has been an absolutely phenomenal conversation. For our listeners who are just getting started on this journey, if you had to give them one piece of advice for building better data pipelines, what would it be?
Just one? That's hard. Okay, I'll say this. Invest in your data quality before you invest in your model architecture. I know it's not as exciting as trying the latest transformer variant, but I have seen time and again that the teams that win are not the ones with the fanciest models. They're the ones with the most reliable data. Your model is only as good as the data you feed it. So build the boring infrastructure first. Make your data quality bulletproof. Set up your contracts, your monitoring, your observability. And then when you layer on a good model, the results will speak for themselves.
I love that. Build the boring stuff first. Priya Ramanathan, VP of AI Platform at Nexus Data Systems, thank you so much for joining us on the AI podcast. This has been an incredibly insightful conversation.
Thank you, Alex. It was a real pleasure. And to everyone listening, if you take one thing away from this, remember your pipeline is your product. Treat it with the respect it deserves.
Beautifully said. And that's a wrap on episode 1 of the AI podcast. If you enjoyed this conversation, make sure to subscribe and leave us a review. We'll be back next week with another deep dive into the world of AI. Until then, keep building, keep learning, and keep questioning. See you next time.